All right, I want to look a little more now at galaxies. First, let's look at the different types of galaxies. And remember, as we look at these, that there may be as many as 1 trillion of these or more in our known universe. So, we said before that for our Milky Way galaxy, if the sun was the size of the little dot on this eye, that the distance across just our one little Milky Way galaxy would go from here to New York City on that scale. And so that's just the size of one galaxy. But imagine now, as we talk about these, we're going to be just kind of throwing around this concept, but just think about how big they are. And that there may be trillions of them in the universe as a whole. So a spiral galaxy then, if we look at it from a top view, has a central nucleus, has a galactic disk, and spiral arms radiating out. Okay, so this is called a pinwheel spiral. And so here the nucleus is in the center. Remember, this nucleus has a higher concentration of stars than normal, but more importantly has what we think is a supermassive black hole in the center. And so then we have spiral arms radiating out. In a pinwheel shape. And if we look at it from a side view, we see a flat disk that the spiral arms are in. So here's the nucleus from a side view. And here are the spiral arms in a flat disk. Okay, so this is our pinwheel spiral. Then we also have the bar-shaped spiral. In the bar-shaped spiral, oftentimes the nucleus may be more elongated. And the spiral arms are more compressed together. Into just a couple of these spiral arms rather than many of them. So if we want to look up at our data projector, we can see here what looks maybe a little more like a pinwheel spiral looked at from a top view. This, of course, is not our own galaxy because we couldn't get far enough away from our own galaxy to be able to get that kind of a picture. But we see there are many galaxies to choose from. Remember, there's more than 1 trillion of them in our universe. So here is more of a pinwheel spiral on the left. On the right, we see here a bar-shaped spiral with the elongated nucleus, and notice that the spiral arms are more compressed. We can look at some variations on this as well. Here is Andromeda Galaxy. That's thought to be a regular spiral galaxy. Here we see a spiral galaxy from a side view. That looks very much like, here's the galactic nucleus, here's the flat disk, but it's actually filled with spiral arms of either the pinwheel or the spiral variety. Here's another one, looked more from an edge-on view. The galactic disk is evident, and that will be the case with spiral galaxies. Here's another one. Okay, so they come in different colors, sizes, and shapes. Here's a couple more of them. And then this is a deep field view, which shows many galaxies here. And what you'll notice, if you look very carefully, we can blow up this thing just a little bit with our magnification. We can see that some of these things look more spheroidal here. These are what are called elliptical galaxies. And these that look like they may have a disk component, although it's not always clear in a picture like this, it looks like some of these are definitely spirals. But perhaps more often than not, what you see are big, huge, ball-shaped objects. And those are called elliptical galaxies. Now, oftentimes these elliptical galaxies don't have a disk component. They're more egg-shaped. But still with a galactic nucleus in the center. And quite possibly an even bigger black hole than we find in spiral galaxies. Now, when we look at the percentage of these things, we find that maybe only a quarter of all galaxies are spirals. And so the majority are elliptical galaxies. Or irregulars. Now, irregular galaxies have no set shape. When we're comparing them to each other, anyway. Of course, it has the same shape as itself, but it has no specific shape that we say is a classic irregular. So if we want to go back here and look at some of these other galaxies in our pictures, here we see an elliptical there. Now, if that versus a spiral here, you notice here this one's elongated more. If it gets more elongated, sometimes it's called lenticular. So it's more of an egg shape. But it still has the galactic nucleus in the center. But the irregulars, what's the deal with those? Well, before I get to that, let me just give you a little puzzle, because I know how much you all like puzzles. Now, when we look out over great distances in the universe, we're also looking backward in time, because the farther out we look, the farther away that light must have traveled to be getting to our eyes today. And so if we're looking out, say, 1 billion light years distance, we're also looking backward in time and seeing the universe as it was 1 billion years ago. And so what we find then, when we look at great distances, we find more quasars, than today. In other words, nearby we don't see many of these active galaxies. And so that's the reason for thinking that quasars might be a galaxy in an early stage of development. Because we're only seeing them at great distances away. I mean, something might have happened. B, what do we see at greater distances? More spiral galaxies. Than today. And so what could this mean? How do we explain this? Well, we could certainly say that if there's more quasars, say, within a billion years after the formation of galaxies, and not so many today, that quasars might be galaxies in a younger stage of development. But how can we justify that? Well, what I think happened with young quasars is that they had a lot of material available to spiral in toward a galactic-sized black hole. But as the black hole formed from the infalling material, the jets basically started pushing on this matter and stopped the inflow. And so the quasar jets shut down. The black hole basically starves itself by pushing outward with this radiation pressure. Eventually the inflow of matter is halted. And at that point, when the inflow is halted, then the galaxy starts forming outward as a disk. Okay, and so we think that this part of our spiral galaxy probably wasn't here when the galaxy first formed, and that this is the result of collisions with other galaxies as well as just material in the disk being converted into stars. And so the galaxy, in other words, the spiral galaxy grows in size, but it becomes less bright. And slowly it grows into the big spiral galaxies that we see, like Andromeda, and we think our Milky Way galaxy is. Now, this probably isn't just generated by one mechanism. The mechanism for the growth one, we think that galaxies eat each other. That if you have a big galaxy eating a smaller galaxy, then the shape of the original galaxy is not too heavily disrupted. And so we can have the spiral feeding, they're cannibals basically, on dwarf galaxies. And we see lots of dwarf galaxies just in our local group of galaxies. You may recall before we said that there are two really big galaxies in our local group. But then there's a whole bunch of others, maybe a few dozen dwarf galaxies. And as a matter of fact, right now, as we speak, the Milky Way galaxy is feeding on the Large Magellanic Cloud. So it's eating it up, and that's helping to create more disk material in our galaxy. So this is one of the mechanisms for the disk growth. Remember, though, that only spiral galaxies have disks. But the second mechanism we think may occur because of essentially galactic weather. We've got the black hole in the center. Here's the jets from it. And so here we have some stars forming. Some of those stars turn to supernova explosions. They blow up, and the material then is pushed outward by the jets. So here's the jet radiation, although it's still happening. It's not happening all the time. It's happening enough for this effect to happen. So you have supernova here, supernova there, but the material doesn't move inward. What happens instead is it is pushed out, outside of the galactic disk, like this, and then eventually, because of gravity, is pulled back, and you get new generations of stars forming out here, and so the disk grows. So basically it's like rain. It's galactic rain. Okay? You've got the supernova material blasting off this way, but you have the jets pushing the material out so that it'll fall like this, and it'll rain back down on the galactic disk here and there, and then that causes the disk to grow. And so our part of the disk we think is new, relatively new, may have only formed in the last 5 billion years. New. But it's still young in comparison to the overall age of the galaxy. And so we think then this kind of galactic weather can also help in disk growth.